S1 Kinematics Example 21. This is the final example in this section, and it's very similar to the ones we've done before. There is a couple of little tricky bits, so I'll go through it in quite a bit of detail. We've got a particle moving along a horizontal axis OX. That just means a horizontal line. At time t equals 0, the particle is at rest and then accelerates at a constant rate. So that means we have a straight line reaching a speed of u. It then maintains that speed for a further 32 seconds. So if it maintains that speed, that's a horizontal straight line. So if we put some labels on our graph, it was accelerating at a constant rate to a speed of u. We don't know what that speed is. And it took 16 seconds. The particle maintains that speed for a further 32 seconds. So read the question carefully, a further 32 seconds, so that's 48 in total. So after the 48 seconds, the particle is at point A, where A is a distance of 320 meters from where we started from O. So this is the speed time graph, and we've got to work out u. Again, they've given us the distance of 320 meters. So we know the area underneath the graph is 320. Using that same formula again, a plus b multiplied by h. So a half of a is the distance on the top, which is 32. B is the distance all the way along the bottom, which is 48. And h is the vertical height, which is the thing we don't know, that's u. Now what we do know is that this will equal 320, so we can make an equation here that we can solve. 32 add 48 is 80, half it, 40. So 40u equals 320, and so u is 8. It's a velocity, so I'll put the units on. Okay. We now have to sketch a distance time graph for the particle. Now, I've actually started the graph further down the page here. In the first section, the particle is accelerating. That means the distance that is covered every second will increase and increase and increase. So we actually get a curve for the first section of the graph, and I'll talk a little bit more about that in a second. We're then going at a constant speed. When something's going at a constant speed, the distance that's covered will increase at the same rate. So it'll go, say, 10 meters every second. And so the displacement from where they started is getting 10 more every time. In other words, it's a straight line. So anytime you've got a constant velocity, the distance will increase at a constant rate, the distance from the starting point. Now, if we think about that first part of the motion, just to do a little bit more analysis, we know that u is 8, and so the acceleration in that first part is change in y over change in x, so the acceleration is a half, and we know that we started from rest. So if we're interested in the distance that we've travelled in that first section, we know that it took 16 seconds. And so we can use ut plus a half at squared. Now I'm going to pretend for a second that I don't know it was 16 seconds. And I'm just going to substitute in the other values that we do know. U is 0, so this will be 0, regardless of the value of t. And then we've got a half times a times t squared. In other words, in this first period of motion, the displacement is given by a quarter t squared. Now, think about the graph of 1/4 x squared, which you will have studied in C1, a quadratic graph, and the quarter is a vertical stretch, factor a quarter. In other words, it just makes it more shallow. So this first part of the graph is actually part of a quadratic graph. Okay, now we know that along here took 16 seconds. So the distance it's gone is a quarter times 16 squared. and that works out to be 64. So on the vertical axis, we can put a label of 64 at the end of that portion of the parabola, the quadratic graph. We're told in the question that the total distance travelled is 320, and we know that in total the motion took 48 seconds. So that completes our distance time graph.